All right, let's dive right into the microscopic heart of, well, everything. We're talking about the invisible, unsung hero that powers your phone, your car, your computer, basically our entire modern world. We are talking about the transistor. So let me just ask you a question. What do you think is the single most important invention of the 20th century? You know, your mind might jump to the airplane, or maybe the internet, or even nuclear power. But what if I told you the answer is something so much smaller? A tiny little component that completely changed the course of human history. And that invention, you guessed it, is the transistor. At its core, a transistor does two really amazing things. It can amplify a signal, kind of like turning up the volume, or it can switch a signal on and off. The name itself, fun fact, is a mashup of transfer and varistor. But for this explainer, I want you to think of a transistor as a digital water faucet. A tiny, tiny turn of the handle can control a massive flow of water. Keep that image in your head.
So, what's our game plan? First, we're going to meet the original gangster, the BJT. Then we'll check out its playbook for making signals bigger. After that, we'll see how it becomes the ultimate on-off switch. Then, we'll meet its slick, more modern cousin, the FET. And finally, we'll see how these little things completely took over the world.
Okay, let's get right to it. We're starting with the classic, the bipolar junction transistor, or just BJT for short. And honestly, the best way to picture how it's built is to think of it as a simple sandwich. I mean, look at this. The structure is surprisingly simple, right? You've got two main flavors, NPN and PNP. The NPN is just a slice of what we call P-type material sandwiched between two layers of N-type. And the PNP? Yep, it's just the opposite. This super simple three-layer structure is the secret to everything a transistor can do. Now, every BJT has three connection points, or terminals: the emitter, the base, and the collector. And here it is, maybe the most important thing to remember about the BJT. It is a current-operated device. Think back to our faucet. A tiny little trickle of current going into the base is like you gently turning the handle. And that small action allows a huge current to flow from the collector down to the emitter. A little bit of current controls a whole lot. So, what can we do with this thing? Well, its first superpower is amplification. And get this, depending on how you wire it up, you get totally different results. It's like having a playbook with three very different strategies for boosting a signal. So here are our three plays. First up, you've got common base. This one gives you a big voltage boost, but no extra current. Then you have the common emitter. This is your all-arounder. It gives you a bit of both. And finally, common collector, which juices up the current but leaves the voltage alone. Each one is a specialized tool for a very specific job. Let's look at that first play, common base. Imagine you have a really weak signal coming from a microphone, just a tiny whisper. You need to boost its voltage to make it useful. Well, this circuit configuration is the perfect tool for that exact job. That's why you see it all the time in high-frequency stuff like radio circuits and microphone preamps. Next up, we have the common emitter configuration. And let me tell you, this thing is the absolute workhorse of the electronics world. It is by far the most commonly used amplifier because it just gives you the best of both worlds. You get solid current gain and solid voltage gain. It's that versatile go-to player you can put anywhere on the field. And our final play from the book is the common collector. Now this one's superpower is a little trickier. It's something called impedance matching. Imagine trying to shout a message across a giant, noisy room to someone who can only whisper back. The message is going to get lost, right? Impedance matching is like giving both of you perfectly tuned walkie-talkies. It makes sure that different parts of a big circuit can talk to each other efficiently without losing the signal's strength. And this table really just sums it all up nicely. As you can see, it's all about trade-offs. If you need a huge voltage gain, you pick common base. If you need a good balance of everything, common emitter is your friend. And if you need a big current boost to match impedances, you go with common collector. It's all about picking the right play for this situation. Okay, so we've seen how transistors can turn up the volume. But what if we just want to turn the signal completely on or completely off? Well, that's the transistor's other superpower. And you could argue it's the one that literally built our digital age, acting as an unbelievably fast, super precise electronic switch. Now, to understand how this works, engineers use a graph that looks like this, called the characteristic curve. Don't worry, it looks more complicated than it is. It's just a map of how the transistor behaves. And for what we're doing now, making a switch, we only care about two specific spots on this map, that area at the bottom called the cutoff region, and the area way on the left called saturation. So these two regions,
Cutoff and saturation are our on and off states. In the cutoff region, you apply zero current to the base. And just like that, bam, no current can flow through the collector. The faucet is completely shut. That's your digital zero. Then in the saturation region, you hit it with maximum base current, and the faucet is thrown wide open. Maximum current flows. That is your digital 1. Off and on. 0 and 1. This right here, this is the fundamental basis of all digital computing.
Now, the BJT was an absolute revolution. But you know technology, it never ever stands still. So meet the next step in the evolution, the field effect transistor, or FET. It does the same job but with a really crucial, game-changing twist.
And here is the key difference. Remember how the BJT was controlled by current? The FET is controlled by voltage. So instead of a little flow of water turning the handle on our faucet, imagine the pressure of the water is what opens the valve. You don't need a flow, you just need the presence of that pressure. This is a huge deal.
And the FET family is pretty big, with two main branches. On one side, you have the JFET. On the other, the MOSFET. And as you can see, it gets even more complex from there. But the one we really care about, the one that really truly took over the entire world, is the MOSFET.
The absolute key to the MOSFET's power is its insulated gate. You see, it's physically separated from the main channel by a microscopically thin layer of metal oxide, which is basically glass. And because of that insulation, it takes practically zero power to control the switch. It's incredibly efficient.
And MOSFETs come in two main flavors, which is super useful for building digital circuits. You've got depletion mode, which are normally on, so you actually have to apply a voltage to turn them off. But the real star of the show is the enhancement mode MOSFET. It's normally off, and you apply a voltage to turn it on. This off by default behavior, well, it's the perfect building block for the logic gates that run our entire digital world.
So we've met the BJT and the FET. We've seen how they can amplify and how they can switch. Now let's put it all together and see exactly why that little MOSFET, that voltage-controlled switch, completely and totally transformed our lives.
So why did the MOSFET win? It really comes down to two things. They can be made insanely, ridiculously small, and they consume almost no power when they're just sitting there, not switching. This made them absolutely perfect for cramming onto microchips. The processor in whatever device you're watching this on right now, it doesn't have thousands or even millions of these little switches. It has billions of them, all firing in perfect concert.
So that's the transistor, a simple digital faucet that, when you multiply it by the billions, created our entire modern world. It's the reason we went from computers the size of a room to computers that fit in our pockets in just a few decades. Which kind of leaves us with one last big question. If this one tiny switch could do all that in 70 years, what do you think the next fundamental building block of our technology is going to look like?